Today's lesson is on complex zeros of polynomial functions. We're going to start by looking at the conjugate pairs theorem. This theorem says that if a polynomial has real coefficients, so a polynomial with real coefficients could be something such as, we'll use p of x is equal to x cubed minus 3x squared plus 9x plus 13. So here's our real coefficient polynomial. If this polynomial has any complex zeros, then they occur as a conjugate pair, meaning that you actually have two. If you have a plus bi as a solution, then you also have a minus bi as a solution. The difference is the sign connecting the real part and the imaginary part. Okay, in the first one you can see you have an addition sign, and the second one you can see you have a subtraction sign. Those are conjugates of each other. So if we use this example that I wrote here, I'm going to tell you that 2 minus 3i is a 0. So we already know that, and I see that the sign here is subtraction. So if this is the case, then we also know that 2 plus 3i is a 0. Okay, those are conjugates of each other. And you could test these in the function, so you could substitute 2 minus 3i or 2 plus 3i back into this function, solve, and you will see that your solution comes out to be 0. If you look at my note sheet, I actually did the work out for that. I'm not going to spend the time doing it right now, but I am telling you that if you substitute in either of these answers, your solution would be 0. Okay, using the conjugate pairs theorem in example 1. So the direction says information is given about a polynomial whose coefficients are real numbers. Find the remaining zeros. Remember from the past unit, if the degree is 5, that means you can have at most 5 numbers, or 5 zeros. And I'm going to label them. So right here we see 1, 0. It's at 1. Then I see another 0 at 5i. Then I see a third 0 at 1 plus I. So we could potentially have 2 more zeros to bring us to 5 zeros. Well, anytime you see an imaginary unit, you need to include the conjugate. So even though 5i is a single term, we still have to include the conjugate. This is technically 0 plus 5i, so we need to include 0 minus 5i. And right here we have 1 plus I, so we would need to include 1 minus I. This would be your 4th 0, and this would be your 5th 0. So finding those two conjugates brings you to match your degree of 5, which is basically what we're looking for. But to answer this question, the remaining zeros would be negative 5i and 1 minus I. So in this type of problem, all you're doing is identifying the conjugate of any imaginary unit that you see. Number 2, the degree is 3. That means we'll have most likely 3 zeros, but we definitely won't have more than that. Here we see 1 0. This is the second 0. The second 0 is 4 minus I, so its conjugate pair would be 4 plus I. There's your third 0. So to answer for remaining zeros, we would just say 4 plus I, and that's the conjugate of 4 minus I. So that's it for problems like this in this example section. You are just identifying the extra or the additional zeros. But if we move down to the next example set, it says to form a polynomial with real coefficients having the given degrees and zeros. So here we have quite a bit to do. We have to first identify all of the zeros. Then we need to multiply them out and report this as a polynomial in standard form. This we have a degree of 4, so at most we'll have 4 zeros, but definitely not more than that. Let's count our zeros. We have a 0 at 1, we have a 0 at 1 again, we have a 0 right here at 4 plus I. But don't forget, we also need this conjugate because whenever you have an imaginary unit, you must include the conjugate. Okay, so just a little note there, it says conjugate pairs theorem. As a reminder, you must include the 0 of -4 minus I. So we change that middle sign. Whoops, I should have labeled that 4. And that gives us the fourth 0. All right, when we list these zeros, I'm just going to start over here and I'm going to make a list. So zeros are x equals 1, x equals 1 again, x equals -4 plus I, and x equals -4 minus I. If these are the zeros and we had to write these as factors, I would write x equals 1 as x minus 1. That way when I solve for x, I would get x equals 1. So think backwards when you're writing these factors. X minus 1 again. So if we need to achieve x equals -4 plus I, we're going to have to write this as x minus -4 plus I, of which we'll distribute that negative sign, and we get x plus 4 minus I. Now think about this for a second. I'm just going to go off on a side note and then I'll come back to answering this. Let's just say we set this equal to 0 and we solve. We subtract 4 from both sides, we add I to both sides. So we get x equals -4 plus I. That's what we had right there. So double check yourself every time. Make sure whichever 0 you write does in fact multiply or simplify, whatever you have to do, simplify out to the original 0. I'm going to put parentheses around this. And notice that I always start with x minus and then I put the factor after that. For the next factor, I have x minus -4 minus I, and distribute that subtraction sign to give me the factor of x plus 4 plus I. Of course, if I set this equal to 0 really quick, x equals -4 minus I. Double check, is that the same? Yes, it is, so we're all set. So when you have these complex factors, always start with x minus and then you list the factor. All right, based on what we just wrote out, we have our four factors of x minus 1, x minus 1, x plus 4 minus I, x plus 4 minus I. I'm going to write these in a polynomial. Now we need to multiply these factors together. We need to multiply all four of them together. But you can only multiply two factors at a time. If you don't remember before we start multiplying, when you are multiplying with imaginary units, don't forget that I squared is going to be replaced with -1. You're definitely going to see that, so important little note right here. Okay, we're going to begin by multiplying the first two factors together, and at the same time we're going to multiply the second two factors together. Then we'll simplify each expression, and then we'll multiply the final two factors together. For the first group, remember you're distributing. X times x, I'll do all of this in orange. X times x is x squared. X times -1 is -x. Oops. -1 times x is -x, and -1 times 1 is +1. Those are your first two factors multiplied together. The second two factors multiplied together. You have three terms in each of these, so this is definitely going to be a little bit more lengthy as an expression. But we're distributing our first value to x to all values in the second set of parentheses. We get x squared plus 4x plus xi, or ix, however you write it. Next, we're going to do the middle term to all terms in the second set of parentheses. 4 times x is 4x, 4 times 4 is 16, and 4 times I is 4i. Next, we're going to multiply the last term in the first set of parentheses. Negative ix, or xi, however you write it, -4i, and -I squared. Now we need to simplify anything we can between these two expressions. So you can only simplify within each one. I'll start with what I did in orange, and I can just highlight quickly and indicate that the only thing I can simplify here are these two terms. So I'm going to simplify this to x squared minus 2x plus 1. As for what I have done out in blue, let's take a look at everything that we can simplify. And I'm going to go term by term. Starting with 4x, or I guess starting with x squared right here, but x squared doesn't have any common terms. So moving on to 4x. 4x can be added right here to 4x, and that's it for variables x. Next, I'm going to look at the xi term. Oops, sorry. All right, xi here and negative xi here. Next, I'm going to look at 4x we already took care of. Then we're at 16, which doesn't have any common terms at the moment, but I have 4i and I have -4i. And then lastly, we have to make a note that we have x squared, which is equal to -1. So don't forget to replace that with a -1. When I start to simplify, remember x squared right here is remaining the same. Next, I have what I highlighted in blue. I have 4x plus 4x, which is 8x. Next, I have what I highlighted in yellow, xi minus xi. These are actually going to cancel. They are just going to form a value of 0. Next, we took care of 4x already, so we're all set with that. After that, we're looking at our constant term of 16, which does remain. Next, we have positive 4i, and then we have negative 4i that we can add together. Those are also going to cancel. They just add to a value of 0. And lastly, we have our value that we're subtracting, but we're subtracting negative 1. So one more time here, we can simplify what's in blue, and I can simplify 16 plus 1, which is going to give me 17. And now lastly, I need to multiply these two factors together. So you can only multiply two factors at a time, which is why we started off by multiplying 2 and 2, and now we have two factors again. So we're going to multiply these for our final answer. You can just watch as I do this so I don't have to talk through every part. It's very similar to what we've already done. I'll of course indicate where I'm at. All right, so I multiplied everything out and I highlighted my common terms. So when I add everything together, I have x to the fourth. 8x cubed minus 2x cubed is positive 6x cubed. 17x squared minus 16x squared plus x squared is going to give us positive 2x squared. Now I'm looking at what's in orange. I have negative 34x plus 8x, and that's going to give me negative 26x. And lastly, I have my constant term of 17. So all of this work to just give you this answer. And you have to be very careful because obviously you can see there's so many rooms for error, and you definitely don't want to be making mistakes, especially when they carry through on the whole problem. So just make sure you go about this really slow. I don't really advise that you skip steps just because it's easy to miss something and then it's kind of gone because the problem is so long. Make sure you do everything out. And remember that you're only multiplying two factors at a time. All right, this last problem, or this last example set, is everything that we did on yesterday's notes. So it's finding the zeros using the P and Q value. But this time you're finding all zeros. You're not just finding the rational zeros. So any zero you can find, this might mean you need to use the quadratic formula. So I'm gonna kind of skip ahead a little bit in here because I know that if I went through all of these, this would end up being a very long video. So I'm going to start by indicating the P and Q values, and then I'm just going to jump right to the ones that are answers. I already did this out ahead of time to find what they are. If you were doing this by yourself, you would have to test quite a few of the values to get to your answer, but here I'm just going to indicate which ones work in your synthetic division, and then we'll talk about what the actual answer is going to be. So I have 3x to the fourth plus 5x cubed plus x squared, 25x squared plus 45x minus 18. So negative 18, or just 18, is our p-value. And we need to list all of the factors. This would be plus or minus 1, plus or minus 2, plus or minus 3. We do not have 4 or 5, but we have plus or minus 6, plus or minus 9, plus or minus 18. Next, we'll look at our Q value, which is 3. Three has two factors, 1 and itself, so 1 and 3. If we list our P and Q value, we would have all of these numbers over the value of 1. So I'm just going to skip writing that as a fraction. That's a lot of work for the same exact answer. And I'm just going to relist plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, plus or minus 18. Next, we would have all of these values again, but now this time we'd have 3 as the denominator. So we have plus or minus 1 over 3, plus or minus 2 over 3, plus or minus 3 over 3, plus or minus 6 over 3, plus or minus 9 over 3, and plus or minus 18 over 3. So we need to simplify anything that is simplifiable or possible to simplify, which is this one here. 3 over 3 is just 1, which we already have, so I'm going to eliminate that value. We can simplify here. 6 over 3 is 2. We already have 2, so we can eliminate 6 over 3. We have 9 over 3, which simplifies to 3, which we already have, so we can eliminate 9 over 3. And 18 over 3 simplifies to 6. We can eliminate that value as well. So our final P or Q list is going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, plus or minus 18, and plus or minus 1/3, plus or minus 2/3. All right, so for the rest of the problem, I'm going to tell you right now that 1, -1, they do not work. 2 does not work. -2 is the first number that I tested that worked. So I'm going to start with that with my synthetic division. Bring down my coefficients of 3, 5, 25, 45, -18. If I bring down the value of 3, 3 times -2, that's -6, plus 5 is -1, times -2 is +2, plus 25 is 27, times -2 is -54, plus 45 is -9, -9 times -2 is +18, which is 0. Okay, this tells us that we know we have a 0 at x equals -2, and we have a factor of x plus 2. Now I can use what's called the depressed polynomial to test the next value. I know that the next value that works, I skip all the way forward to positive 1/3. And I'm testing this with my depressed polynomial, 3, -1, 27, -9. I know this is a fraction, but notice that the denominator is 3, and then notice that all of these, with the exception of 1, there are factors that have a divisor of 3, so it's going to work out nice. We're not really going to end up with any fractions here. Bring down the 3. 3 times 1/3 is just going to be 1. -1 plus 1 is 0. 0 times 1/3 is 0. 27 plus 0 is 27. 27 times 1/3. 3 goes into itself once, goes into 27 9 times. 9 plus -9 is 0. This tells us that x equals 1/3, and also that x, so this is kind of weird to write, but x minus 1/3 is your factor. Of course, you could multiply out that divisor if you want to, but I'm just going to leave it as a fraction. This is perfectly fine, and it's the fastest, so I'm going to leave it like that. I still have a depressed polynomial, but at this point I'm going to write it as a factored expression because my depressed polynomial is down to 3 terms, which means it's a quadratic, and we can factor quadratics using a more basic method. So f of x is equal to our first factor of x plus 2, our second factor of x minus 1/3, and our last factor, which is the expression left in the synthetic division, so it's the depressed polynomial, which is 3x squared plus 0x, which I'm not going to write, plus 27. We're finding all zeros. I already know the first two. I know that x is equal to -2. I know that x is equal to 1/3. This last one, 3x squared plus 27 is equal to 0. Subtract 27 from both sides. 3x squared equals -27. Divide both sides by 3. X squared equals -9. Square root both sides. Hopefully you all remember if you have a negative sign underneath the square root, you can simplify that as the imaginary unit. So this right now simplifies to plus or minus I times the square root of 9. But just to go even further, x is equal to plus or minus the square root of 9, which is 3 times I. So here's your, in this case, 4 solutions because this counts as 2. We have x equals plus or minus 3i, and then plus or minus just -2, not plus or minus, just -2, and just positive 1/3. Here is your final answer. And that's it for this problem. I'll post my answer, or if you keep watching, I'll put my answer up here. Not gonna talk through it. I think I'm just gonna post it or what it is. Actually, you know what? I'll just do the problem out, but I won't talk through it. So you can watch the video to see the next problem, which does involve the quadratic formula.